Hi, I'm Conrad Watt, and I'm here today to talk about our paper, Repairing and Mechanizing the JavaScript Relaxed Memory Model. So modern JavaScript has a reputation for being a single-threaded language, or at least a language where all concurrency is done through message passing. However, JavaScript does provide access to true shared memory concurrency through the shared array buffer object. Most JavaScript objects interact frequently with JavaScript's complex dynamic behavior and inheritance model. However, shared array buffers are incredibly simple and low level. When you declare a shared array buffer in JavaScript, you are literally allocating a simple linear buffer of raw bytes. References to this buffer can then be sent to multiple threads which can access the buffer concurrently. These accesses themselves are very low level, generally corresponding pretty precisely to individual accesses in the underlying architectures. Because this feature is so low level, JavaScript programs using it can exhibit relaxed behaviors. This means that a concurrent program may exhibit results which cannot be explained by a naive sequential interleaving of its individual accesses. So here's a simple example. The code on screen is the well-known message passing test. A shared array buffer is declared, zero initialized, and then sent to two threads. The left-hand thread writes to index 0 and then to index 1. The other thread attempts to observe these writes. First, in the highlighted code, it checks whether it can see the write at index 1 by reading a value of 1. Only if it succeeds, it then tries to read index 0. In the naive, sequentially consistent model, y will always equal 1 if the conditional is executed. However, when running the code on real hardware, it's very common to see the result x equals 1, y equals 0. So this is a very simple example of relaxed behavior, which may have been caused by compiler optimizations or microarchitectural reorderings during execution. So, if we want to specify which relaxed behaviors are allowed and which are forbidden for a given program, we need a semantics with a relaxed memory model. The JavaScript specification already defines a relaxed memory model based on the existing model of C++11 with some minor modifications to handle programs with mixed size, partially overlapping accesses. This is the model that we are investigating. The JavaScript specification defines two levels of semantics. First, a familiar thread-local operational semantics. However, when executing a concurrent access, instead of picking a concrete result, the thread-local semantics simply emits an event recording the access and continues execution. The second level of semantics is the axiomatic memory model. This looks at the set of events generated by a given execution of the thread-local semantics. This set of events, together with ordering constraints derived from the thread local execution, is called a candidate execution and is classified as either valid or invalid. At the top level, the specification states that a correct implementation of the language must only exhibit behaviors which correspond to valid executions in the model. So here's a concrete example, the program we just looked at, the MP program. We're interested in the execution where x equals 1 and y equals 0. So here is the candidate execution which is generated by the thread local semantics. Note that there is an event corresponding to each concurrent access, including the 0 initialization at the start. The HB arrows represent happens before constraints. These are strong ordering guarantees which the model must keep track of. In this case, they're just representing program order. At the top level, we show an execution is valid by finding something called a reads from relation, which associates every read event with a justifying write, which explains how it was allowed to read the value that it did. However, this reads from relation must be consistent with happens before, in a way we will define precisely in a minute. So here's the read from relation, which is the only possible justification for the program's outcome. Each read event is matched with a write event to the same location with the appropriate value. So here's what the model must check in terms of happens before. A candidate execution is not valid if either of these two shapes appear. Now the first shape ensures that a read may not get its value from a write that takes place in the future according to happens before. And the second shape ensures that a read cannot read from a stale write if there is a newer one on the same location, again in terms of happens before. So in fact, our proposed execution doesn't have either of these shapes and the model declares it valid, therefore this outcome is allowed by the JavaScript specification. Now we can modify the program to forbid the outcome by changing some accesses to atomics. JavaScript offers one kind of atomic operation, unlike C++11, which has several. Atomics generate specially distinguished events in the candidate execution. If an atomic write and read of equal size are associated by reads from, a special synchronizes with edge must be added, which is defined to imply a happens before edge. Therefore, the same execution of the revised program with the extra atomics is forbidden, as the read of 0 is now coming from a stale write, according to happens before. So I'm not going to be discussing every rule of the model here, only what's relevant to the examples I want to show in this presentation. Now with that being said, atomic operations must obey some ordering constraints beyond just the synchronizes with one that we already described. So aside from reads from, the JavaScript model requires the definition of a total order relation over all events, such that this shape is forbidden. Now this is intended to further strengthen the behavior of atomic operations. However, this condition is a little too strong as it's stated here, since it also ends up constraining non-atomics, since the middle write W was not required to be an atomic. Now this emerges as a compilation scheme correctness bug. So let's set the scene. We want to prove that concurrent JavaScript programs can be successfully compiled to ARMv8, which itself has a very similar axiomatic memory model. Now the proof of this requires us to show that for every possible valid ARMv8 execution for a compiled JavaScript program, the equivalent behavior is allowed by the JavaScript memory model. So let's look at how this mistake in the atomics condition mentioned earlier turns into a counterexample to this property. So here's the counterexample program in JavaScript, and we're going to look more precisely at it later on, but the important high-level point here is that the model does not permit the program to end with the result x equals 1, y equals 1. So here's the same program, but compiled to ARMv8. Now this architecture, the ARMv8 architecture, has special instructions, the LDAR, STLR instructions, which are designed to efficiently implement C++ atomic operations. Now at the very least, Chrome's JavaScript engine, V8, uses this compilation scheme. The ARMv8 memory model says that this outcome is allowed, meaning that a JavaScript program compiled to ARMv8 can exhibit an execution which is forbidden by the JavaScript memory model. Now I won't go into the formal details of the ARMv8 memory model here, but at a high level, ARM allows these two highlighted instructions here to execute out of order with each other. If the two instructions are swapped, then the outcome is possible just by looking at a naive sequential interleaving of the instructions. So to see why this outcome is forbidden by the JavaScript memory model, we need to do a little logic puzzle. So here's the candidate execution corresponding to the forbidden outcome. We pick the only choice of reads from that's possible, and the tot edge over to the right is already implied by the happens before edge in the same direction, which just comes from program order. So let's ask the question, is it possible that there's a tot edge in this direction between these two highlighted events? By the sequentially consistent atomics rule that we looked at earlier, the answer must be no, otherwise the highlighted right would be stale. Since tot is a total order, then there must be an edge going in the other direction instead. Now because of this, some other tot edges are instantly and directly implied by transitivity of tot, combined with HB being a subset of tot. However, if we add these mandatory tot edges in, then we form one of the forbidden shapes, the forbidden sequentially consistent atomic shape, using these three highlighted events. Therefore, we know that there is no way for us to construct a valid execution, because we've now gone through every possibility, and the outcome must be forbidden. And the fix is simple enough. We just relax the sequentially consistent atomics rule to not cover non-atomic accesses, because the thing that makes this execution forbidden here is the fact that the shape we form at the end has a non-atomic access in the middle. There are other issues with the JavaScript model, which are known about from previous work. Our corrected model also incorporates a fix for a violation of the SCDRF correctness condition. I won't go into detail about it here, but it is described in the paper, and I've put a citation here to the other paper that originally presented that issue and suggested a fix. There is another significant problem with the JavaScript memory model, which we aren't able to fix. The JavaScript model suffers from C11 style thin air executions. This maybe isn't surprising, since their models are very similar. The existence of these problematic executions is a well-known issue in our field, and we don't make any headway as part of this work. This issue doesn't prevent us from proving compilation scheme correctness, but it is widely agreed that thin air executions are undesirable, and we should eventually find a way to get rid of them. The ARMv8 counterexample we described earlier was found automatically using model checking. We had originally discovered a larger counterexample by hand, which was the genesis for this work. We follow the methodology of the existing memalloy tool in generating counterexample executions using the alloy model checker. In order to allow the JavaScript and ARMv8 models to be directly compared, we made a best effort extension of the ARMv8 model to make it handle mixed-sized accesses, supported by extensive validation. At the time, ARM had not published an official mixed-sized axiomatic model, although since then the situation has evolved. JavaScript's handling of mixed-sized accesses is very basic, so it's likely that if there are discrepancies between our model and an official ARM mixed-sized model, they will be in areas that are not relevant to our proofs. We plan to investigate further. To successfully complete a compilation correctness proof, we need to define a relation between the JavaScript and ARMv8 executions, which preserves validity from ARMv8 to JavaScript. We were able to rapidly iterate on this relation in Alloy, checking up to a bound that it was correct, effectively carrying out our compilation correctness proof up to a fixed bound. Once we had built confidence in our corrected JavaScript model and in our proof strategy, we fully mechanized and verified the relevant properties in Coq. In addition, for a subset of JavaScript with no mixed-sized accesses, we plug into the existing intermediate memory model proof infrastructure, getting us a number of compilation scheme correctness results for free. And all of this being said and done, our corrected model was adopted into the JavaScript standard. In terms of future work, there are still some outstanding matters that should be investigated. First, our work has focused purely on the direct mapping of source language access to assembly access. We have not yet investigated compiler optimizations. Secondly, it's likely that JavaScript will one day be extended with weaker and more efficient release-acquire atomics. We hope to be able to use our model to inform their development. Finally, we've not investigated a mixed-sized compilation correctness proof for x86, which is arguably JavaScript's biggest platform. We're limited here by a lack of research into x86's mixed-size semantics. So that's it from me. I hope you enjoyed the talk, and I'm happy to take questions.